Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 4, Section 1, Chapter 2, Topic 4, Part 2.
Common failure modes in semiconductor packaging. A.
Solder joint cracking. Thermal cycling and mechanical loading can induce fatigue and cracking in solder joints, leading to electrical discontinuity and device malfunction.
Solder joint cracking is a common failure mode in surface mount technology (SMT) packages, flip chip packages, and ball grid array (BGA) packages. B. Die cracking. Mechanical stresses from thermal expansion mismatch or mechanical loading can cause cracking in semiconductor dies, resulting in device failure. Die cracking is often observed in large die packages, high-power devices, and devices subjected to mechanical shock or vibration. C. Delamination. Delamination occurs when adhesive layers separate from substrate or encapsulant materials due to thermal cycling or moisture ingress. Delamination weakens package integrity, compromises thermal dissipation, and increases the risk of die detachment or electrical shorts. D. Wire bond failure. Mechanical stresses from thermal cycling, vibration, or mechanical loading can cause wire bond detachment or fracture, leading to open circuits or device failure. Wire bond failure is prevalent in wire-bonded packages, such as leaded packages and chip-on-board (COB) assemblies. E. Package warpage. Thermal stresses from temperature variations or uneven cooling can induce package warpage, affecting electrical connectivity, thermal dissipation, and reliability. Excessive package warpage can lead to solder joint failure, die cracking, and reliability issues in semiconductor packages. Mitigation strategies. To mitigate failure modes driven by package mechanical behavior, semiconductor manufacturers employ various strategies, including a. Material selection. Choosing materials with matched coefficients of thermal expansion (CTE), high mechanical strength, and excellent adhesion properties minimizes thermal stress and mechanical failure risks. B. Design optimization. Optimizing package designs to reduce stress concentrations, distribute mechanical loads evenly, and enhance structural integrity improves reliability and performance. C. Process control. Implementing stringent process controls, such as optimized assembly techniques, precise molding parameters, and thorough quality assurance protocols, minimizes defects and enhances package reliability. D. Reliability testing. Conducting comprehensive reliability testing, including thermal cycling, mechanical shock, and environmental stress testing, validates package performance and identifies potential failure modes. Conclusion. Predicting failure modes driven by package mechanical behavior is essential for designing reliable and robust semiconductor packages. By understanding the sources of mechanical stress, employing predictive modeling techniques, and implementing mitigation strategies, semiconductor manufacturers can optimize package designs, enhance reliability, and ensure the long-term performance of electronic devices. Continued advancements in predictive modeling, failure analysis techniques, and reliability testing methodologies will further improve the reliability and durability of semiconductor packaging in the future. Thanks for watching.
Please like, share, and subscribe.